Let's look at another example where we wish to determine the intervals of increase and the intervals of decrease for a given function. So here's an example. Notice in this case, the domain is not all real numbers, but in fact only includes 0 and goes out to infinity, right? Because we can't take the square root of a negative number. So again, it's always a good idea to identify the domain of your given function before we go any further in determining where the function might be increasing or decreasing. What I want to do is partition this and determine in this domain the transition points. So where the function is going up and where it's going down. Again, we use the power of calculus. So remember that all of the transition points are guaranteed to be among the critical values. Okay, and then we, of course, use the first derivative test to determine whether or not those critical values are indeed transition points. Let's go ahead and compute the derivative because, of course, we have to have the collection of critical values first, and we know the critical values include where the function, where the derivative is 0 or where the function's derivative might not exist. So let's take the derivative of this function. So the derivative of f of x is given by, well, this is just a power rule in each case. It's 1/2 x to the minus 1/2 minus 3/2 x to the 1/2, right? Now, in this kind of situation, it's best to write this in terms of one common denominator, one fraction, because that'll help us determine where the critical values actually are. Okay, so let's do that. Again, notice this is the same thing as 1/2 roots of x minus 3 root x over 2, right? Got a negative exponent, a positive exponent. A common denominator, you can already see, is going to be 2 root x, right? This one doesn't need anything, but this, of course, term requires root x multiplied on top and bottom, so I get 3x. Okay? So now I've simplified this. And this will help us determine where all the critical values are. You can easily see where they are, in fact, right? Obviously, we have a critical value where the derivative is 0. Well, the derivative is 0 when x is 1/3, right? That's where the numerator is 0, but the denominator is not 0. The square root of 1/3 is a number, after all, and so I'd get a number down below, but on the top I'd have 0. So I know the derivative here is equal to 0 when x is equal to 1/3. And I can see that by just setting the numerator equal to 0, right? If I set 1 minus 3x equal to 0, you can see your x is going to be 1/3. Okay, you can see that without doing much work. Also, we know there's in fact another point, another critical value, right? We also know that critical values occur where the derivative is equal to, or does not exist, I should say, right? Well, look, here's the derivative function. Notice that this derivative function does not exist at one particular value in the domain, right? In particular, if x is equal to 0, we have a problem, right? So, in fact, x equals 0 is another critical value. So we see that f's derivative at x, it does not exist. Okay, when x is equal to 0. And the point is, this is why it's important to look at the domain of the original function, because this point is in the domain of this function. So it's important to know this is a critical value. So now I've listed the critical values here. I still have this derivative because this is going to be useful for the first derivative test, of course. So now again, what I'm able to do is partition this domain into or around these critical values. Well, in this case, actually 0 was at the edge, so there's not really much I can do there, right? So in many ways, I don't really include anything below 0, right? The domain only includes points from 0 out to infinity. So in this case, I really only need to look at this one value here. But you could see the domain is partitioned into two intervals, right? From 0 out to, and I should use the round bracket here, from 0 out to 1/3. Okay, that's this part. And of course, the other one is from 1/3 out to infinity. That's this other part. Okay? Even though there were two critical values, well, that critical value is right at the edge of the domain. Okay, so I just know something critical happens there, but again, it's only this 1/3 that may or may not be a transition point. Let's go ahead and look. Let's test. So again, I pick test values in these two intervals. Well, in this interval, we want to pick something as easy as possible. It looks like if I want to pick something halfway or in between somewhere, maybe an easy number would be 1/2. That's probably the easiest test value we could try. So let's try a test value of 1/2. Similarly, between 1/3 and infinity, again, you want to pick the easiest number possible. Let's pick a whole number. In particular, the easiest whole number here would probably be 1. Let's try 1. Okay? So again, what we do is we test each one of these values by putting them into the derivative and determine the sign of the corresponding derivative, right? Well, look, if I take the derivative and I put 1/2 in for x up here, what do we get? Well, let's look. We get 1 minus 3/2. Okay, well, that means 1 minus 1/2 is going to be a negative 1/2. So this is a negative 1/2 on top. And on the bottom, we get 2 roots of 1/2. Well, that's positive, right? 2 roots of 1/2. It doesn't matter what that number is. I know the bottom or the denominator is positive. The numerator is negative, so the overall number is negative, right? So it's negative. That's all that really matters. So again, if I write f prime on top, I know that the function is, well, the derivative is negative here for all the points in between 0 and 1/3. And similarly, to determine what the derivative is for the other interval, I just go ahead and test it in the first derivative. So f prime at when x is 1, again, put 1 in here, I get 1 minus 3 over 2 times root 1. Well, notice that the bottom is always positive, but the top is actually negative, right? It's negative there again. So it turns out the derivative is negative there. In some sense, even though 1/3 is a critical value, this was a false positive. One of those cases where, even though we had a critical value, it was not a transition point, right? Because we know now, if I finish this derivative test here, if I'll write down what f is doing down below, I know that f is decreasing from 0 to 1/3, but then even after 1/3, from 1/3 out to infinity, the function continues to decrease, okay? So that means that, in fact, in this case, even though we had these 2 critical values, this function does not have any transition points. This function is actually increasing on its entire domain, okay? So that means when all the smoke clears, I can tell you about where this function is increasing and decreasing. I would say the original function, right? We're going back to this original function. F of x is decreasing on its entire domain from 0 out to infinity. In fact, we would just probably go in that direction, okay? So that means that, again, even though I have critical values, it does not guarantee those critical values really are transition points, okay? But I have to test them using the first derivative test.